Good. So for those of you who don't know me, I am Hal Finkel, and I'm going to talk to you about parallelization in LLVM, optimization, and a whole bunch of related things. Before I do that, let me say that the work I'm going to be presenting is the product of multiple people. Some myself, a lot of it Johanna Stuffert, who's been working with me now for the last month or so, Shinmin Tian from Intel, and George Steele from Los Alamos National Laboratory. And I'll sort of call out which parts are primarily whose work at the time. OK. So some of you have heard me talk about some of this before. I think last year at EuroLLVM, I provided some motivational material in my talk then. And so this is, in some sense, kind of an update. But it's a good kind of update because it's an update with data, which is always a nice kind of update to have. And also, but even though it is an update with data, I'm going to start with the non-data part first. Because while I'm going to present some data and I'm going to talk about some challenges that we've come across and kind of explain the nature of those, I do want to step back at first and say something about what the problem is and why we think it's going to get worse in the future. So what's the problem that we have? So the problem that we have today is that we have constructs that our programmers need to use to introduce parallelism into their applications. The most common set of constructs we have today are the ones that come from OpenMP. Clang and LLVM support OpenMP, mostly Clang, as I'll explain in a moment. And Clang has an OpenMP runtime library. And this OpenMP runtime library does things like create threads and run different portions of code in different threads. It has a whole bunch of different constructs to handle different aspects of concurrency, parallelism, et cetera. And now OpenMP also has an additional set of features that enable us to target various kinds of accelerators. And in LLVM and Clang, we now have support for targeting GPUs, for example, NVIDIA GPUs with OpenMP target offload. And that comes with its own device-side runtime library in addition to the host runtime library. Various people are investigating porting this implementation to other kinds of GPUs and other kinds of accelerators. So we're seeing this. And one thing that's sort of interesting about this is that it's changing the way that people write OpenMP code. And the reason why this is changing is because of the different hardware model. So most of the OpenMP code that we see today has very coarse-grained parallelism. And this is because threads on CPUs tend to be very heavyweight objects. At least operating system threads on CPUs tend to be very heavyweight objects. And so anytime you invoke operations that rely on creating or even waking up a large number of operating system threads, these operations tend to be very expensive. And so to amortize that cost, you need to be doing a lot of stuff inside the parallel region in order to amortize the cost of creating or even waking up large numbers of CPU OpenMP threads. So, but that model doesn't necessarily apply to GPUs and other kinds of accelerators, where you can create a lot of threads on GPU. These might be SIMT threads or what have you, at relatively low cost compared to what you can have on a CPU sometimes. And in those cases, you may end up with much finer grained parallelism. And thus more opportunity and more expectation on the user's part that the compiler is going to do more to help you optimize that code. So that's one thing to point out. So aside from that, we have two other things. So one is that OpenMP itself is changing. And OpenMP itself is changing in a way which I think is very exciting. And the reason is that historically, OpenMP has intermixed two different kinds of concepts. It's intermixed the concepts of semantics, where the user gets to specify things about their code, with a sort of prescriptive set of ways in which the compiler and runtime should parallelize pieces of code. This is good in some sense. It allows users to tune things in a way that makes sense for their application. But it's also very constraining on implementations. And as hardware has changed, and interesting hardware looks less and less like CPUs with a few cores running heavyweight threads, we've discovered that the fact that people have codes that they can tune for that kind of architecture is less interesting than allowing the compiler to perform more invasive and thus more profitable transformations. So one thing that the OpenMP language committee is considering, and in fact may end up in version 5 of that standard at the next meeting, is to add a construct that is, in some sense, purely semantic. So it adds a construct which says, this loop is data parallel, and do stuff with it. So this is actually kind of interesting, but it means that there's not really a good way for a front end by itself to make a good decision about what to do with that. Unlike the way Clang handles OpenMP right now, where it essentially in the front end translates all the directives into runtime calls, you really don't want to do that for this, because there's lots of different ways that you can translate that, and you probably want to analyze what's inside the region in order to figure that out. A story, which is not 100% true, but is kind of true and amusing nonetheless, is the naming debate over this construct. So it's inspired by the OpenACC directive that's called independent. And originally they didn't like that, so they said they would name it concurrent. And then they realized that now they had a terminology problem because they got everything backward. Because in OpenMP, the way you designate a concurrent loop, I mean something that would be concurrent in the sort of computer science literature sense, is that you say parallel. And so they said, well, OK, so if parallel means concurrent and concurrent means parallel, that's good because they don't overlap, but now they have everything exactly backwards. So they decided, I think, at the last meeting not to call it concurrent and to go back to just borrowing the word independent from OpenACC. But so this is something that is likely to end up in the next OpenMP standard. And it's going to imply that we want the optimizer to do more analysis to figure out what to do with that thing. The other thing that's changing is that we're seeing a lot of users start to use OpenMP indirectly through C++ abstraction libraries. And while there's nothing inherent in using abstraction libraries that dictates how coarse or fine-grained or parallel regions are, the coding patterns that we tend to see in the use of these libraries tend to be more fine-grained. And that's for two reasons. One is because it's in some sense natural given the formulations of these things as algorithms. I mean, OK, you can make coarse or fine-grained for each things. But if you have more complicated algorithms, the things you put inside the algorithms tend to be smaller. And the other reason is that it goes along with a general restructuring of code that people are doing to make better use of abstraction patterns and not have everything in one big function, which is good. And we'd like to encourage people not to have all their code in one big function. So, and as a result, the uses that we see here tend to be more fine-grained. Because you're trying to isolate logic that has to do with some particular classes or some particular set of data structures in pieces of code that are not the same pieces of code as code that deals with other data structures and variables. And so the way that people tend to write these down is using algorithms. Here's our list, by the way, of C++ 17 algorithms, which in theory can be parallel. And these things tend to be more isolated to the to the class hierarchies and pieces of code that where those data members are otherwise defined and accessed, and this is really nice, but means that now we're putting a lot more pressure on the optimizer in the implementation to reduce what we now see as abstraction penalties. So if you have all of your code in all of the sort of parallel code in one big function, and you just have a few directives that say, oh, by the way, run this function in parallel, then there's not much overhead, and there's not much for the compiler to do. But of course, if the parallelization constructs are now spread all over your code, and they only appear next to each other or sort of otherwise amenable to optimization after you do function inlining and other kinds of analysis, well, now the compiler actually has to do that stuff in order for users to get acceptable performance. In principle, we would also like to think that this aids in what we call performance portability, right, which is the ability to write code using, well, in this case, parallel constructs, and have that code perform well on different kinds of architectures. Obviously, that's the goal of a compiler. And that's an important goal. But actually, another really important goal, and one which we already see being important in practice, is just to enable users to write code using appropriate levels of abstraction. And this is an important thing that we're hoping to enable. OK. So let me talk about some of the challenges that we see and some sort of optimizations you would like to be able to perform, why sometimes they don't get performed, and also why sometimes introducing parallelism into your code, especially in the way it's done now, can actually lead to performance degradations instead of speedups. All right, so I'm going to go through these somewhat quickly. So one is variable capturing. And again, this is as a side effect of the fact that Clang right now and many other implementations tend to lower parallelism constructs in terms of runtime calls. This means the optimizer has to be very pessimistic about what those calls do, because the optimizer doesn't understand what those runtime calls do. And so here we have a couple of relatively simple examples. So one is here I have a loop. There's a variable up here, which is y, which I've set to a constant. I have some code here, which doesn't change what y is. And then I have some call here, which is not inside the parallel region. And so I would like the knowledge that I've set y here to this constant to be propagated through the code. For obvious reasons, this is the basic optimization we like to perform. And what you find in Clang, for example, is that once you put this parallelism construct here, this propagation doesn't happen anymore. And it's not just that it doesn't happen inside the parallel code. It doesn't happen after the parallel code either. So the performance here will essentially degrade for the entire function. It's not just a problem with the parallel code. GCC actually has a slightly smarter way of doing this internally and catches this right now. But this is what we'd like to end up with is sort of the constant propagation in both cases. And this is, in fact, something that we can do. We can have an optimization pass which recognizes this pattern. And essentially, it can analyze the code, figure out that you're not changing y in this case. And then it can make a sort of separate copy that gets captured by the runtime. And so long as that happens, now this doesn't affect the constant propagation. But of course, it also relied on the fact that we had some optimization which understood the runtime calls and their semantics and could perform this kind of optimization. We have another sort of interesting set of things that we've run into is, again, when you take this code and you outline it, you lose a lot of the aliasing information that the optimizer otherwise had in the thing that is now the caller of your outlined parallel region. Restrict qualified pointers are a big one. One of the things we found that was interesting here is that you have to be very careful when you start inlining and sort of mucking around with the parallel regions when they include restrict qualified pointers. There are a couple of ways of potentially dealing with this. One of the things about the way that LLVM's current implementation works is that, OK, so restrict here turns into the no alias attribute on functions. And when you inline functions that have no alias on their function arguments, the inliner actually goes through and takes out the no alias and adds a bunch of no alias metadata to preserve the no alias information only in the scope of the now inlined body of the function. When you start messing around with the outlined parallel regions, you end up having to do something very similar. Although the no alias metadata may not be the sort of most succinct representation of this. So this is one of the things that we have to work out is how to actually make this work in practice in a way which is sort of easiest on the optimizer and everything else. But here, just as a sort of quick example, one thing is, though, if you have a restrict qualified pointer, and then you have one thing to realize is that the barrier constructs here, the way that LLVM models dependencies right now is essentially all as memory dependencies. So barriers work because they look like arbitrary functions that may write or read anything. But of course, if you have a restrict qualified pointer, you've promised that nothing else is writing or reading that, including the barrier. So the barrier here doesn't really have much of an effect within the region. And this kind of works today because the restrict, if it gets applied to the whole outlined region, and there's always an implicit barrier at the end of the outlined region. So we have a sort of set of circumstances which cause this to be correct. But as soon as you start performing optimizations on this, you immediately run into the problem that you have to deal with these things explicitly. One of the things that we've experimented with is sort of taking these things and adding them on sort of operand bundles on the barrier calls, which may be a sort of useful way of doing this. We could also add no alias metadata. We have a set of let's see if I get the barriers here. So as I'm mentioning the barriers, one of the sort of interesting cases where you end up with barriers that you would like to eliminate is when you start combining parallel regions. And here we have a sort of quick example of this, where here we have, so here we have a parallelizable loop. Here we have another function that has a parallel loop. And the way OpenMP works is every time you hit one of these parallel regions, you have to go and create and/or wake up a bunch of threads to do work. And this may not be what you want to do in some context. So for example, if you have code that looks like this, which you'll see later, we have a benchmark that looks exactly like this, then here you have a number of these functions that are called. And in each of these functions, you have some parallel region. And so what's happening here is, for each one of these iterations, you're waking up and then joining threads multiple times. And of course, on sort of traditional multi-core machines, if you're waking up 4 threads or something, I mean, that's unfortunate, but it's not the worst thing in the world. But of course, on many core machines, you can easily have hundreds of hardware threads, and if you oversubscribe, you can have even more. And on other kinds of architectures and accelerators, you can have even more threads than that. And this sort of just becomes very undesirable. So what happens is, so if you so if you take these functions and you sort of inline them at the top level, now you can see that here we have these different parallel regions and each one implies a sort of fork and join and barrier and all sorts of other nice but fairly expensive synchronization constructs. And so you say, okay, well, that's not good. So what you would like to do is have an optimization that kind of rewrites this to use one parallel region, and you want it to analyze the code here to figure out when you can eliminate the barriers. So here's the transformation that you like to perform, right? You want to have one parallel region, and you want to have sort of just the individual work sharing constructs there. And then based on some analysis of the code, you can figure out, oh, I can eliminate the barriers. Oftentimes, the runtime savings comes from doing both of these things. And so, okay, so we can essentially eliminate the barriers here. And now you have a very efficient implementation. But the point that I was making earlier, and I think this is a really good example of that, is this kind of thing is not what we want users to do by hand. The fact that the code in those functions with parallel was a function of the code in those functions. And moreover, the fact that those functions are used in a place where you can elide the barriers at the end of those parallel regions is not something that you want to have as an implicit contract between the caller and the callee of each of those functions. But in optimized code that we have today, we have a lot of that. Or we have a lot of implicit contracts, neither of which are good. And so what we would like is to be able to have the compiler do more of these optimizations. So we've done a bunch of experimentation. There are obviously lots of different ways that you can represent parallelism within LLVM, within LLVM's IR. We already have a representation today. We have a bunch of runtime calls and some other things. And it is certainly possible to construct optimizations using that representation. And moreover, we consider that kind of the baseline representation, because that's what we have now. We can make things work on that representation. There may be others that are better, and I'll tell you about some experiments we've been doing on some potentially better representations. But in the meantime, as we look at these various things, we have to analyze different factors that are relevant. So one is for each of these different representations, we want to look at the cost, right? Both sort of implementation cost and also compile time cost, maintenance cost, other kinds of things like this. We'd like to look at the effectiveness of the different representations. What kinds of operations do different representations make easy or hard? And we would like to look at kind of reusability across different programming models. I mean, we are very interested in OpenMP. OpenMP is certainly the most common parallel programming model that we have right now. It is not the only one. We have a significant number of users who use OpenACC, for example, very similar to OpenMP. We are starting to see users who are interested in adopting C++ parallel algorithms, and we have some users who use just sort of other parallel programming models. I know we have some people who have experimented with Silk. We have different programming models that are specific to GPUs and other kinds of accelerators. So and you don't want to write very similar optimizations on each of these programming models separately. That doesn't make sense. And so we're trying to understand how these things fit in, what kind of constraints they impose on the programming models you can handle and on the rest of the optimizer. So that's sort of what we're doing. And this is work that Johannes has been working on. So here what we've done is we have created experimentally an abstraction layer over different kinds of parallel IR representations, different types of representations in LLVM and extensions to LLVM. And on top of that, we have implemented some of these experimental optimizations. So they do things like if you analyze a parallel region and you discover that it doesn't change the value of some variable that's passed in a way that is observable after the region ends, then you don't have to get it back, right? So you can have a private copy in that region. This has a nice interplay with optimizations that propagate aliasing information from the outside the parallel region into the parallel region. We have what we call region expansion, where you take your parallel regions. You can take, well, if you take multiple, essentially consecutive parallel regions, you can merge them into a larger parallel region, eliminate some of that thread startup, shutdown overhead. And this has a strong relationship to the barrier elimination, because these parallel regions have implicit barriers. If you merge them, then you put in an explicit barrier, but you don't want the explicit barrier, so you want to try and remove that. Users can also write barriers in various places that sometimes have to be removed. This is less common, but happens nonetheless. And so on top of these things, I should say underneath this abstraction layer, there are a couple of different things that we've been looking at. So one is directly operating on the runtime calls that Clang uses for LLVM's OpenMP runtime library. You can do the same thing on top of, say, GCC's runtime library or any of the others. We've been looking at a set of IR extensions that Intel has been working on for some of their internal work that they've shared with us. This is just starting now. We've been looking at an implementation based on Tapir. I'll talk about that in a moment as well, which is a project that originally came out of MIT and has now been experimented with by a number of groups, including our group at Los Alamos National Laboratory. And so, we have a bunch of things. And right now, what we have working to collect data are implementations based directly on our runtime calls, and then some things that are built on top of Tapir. So that's kind of where that stands. Let me just sort of provide you with one more example, which you may be able to read from here. But this is one of the Rodinia benchmarks. And again, so here we have a parallel region. It has a work sharing for loop in here, and it uses this double buffering scheme in order to compute multiple iterations and obviously not have a separate memory buffer for each iteration. So you keep the current in the last one and then you swap. It's actually a quite common idiom, but one which tends to foul up optimization of loops that use this. And what we can see here is that applying these optimizations, the ones that I talked about, the attribute propagation, the privatization to that loop, result in a significant decrease in runtime for this benchmark. And this is essentially because when you apply those optimizations, you privatize these variables and you propagate aliasing information in, and you allow the optimizer to understand a lot more about the aliasing properties of these arrays. When the optimizer knows nothing about these arrays and thinks they could point to anything, then you don't get much optimization. OK. So that's obviously quite nice. Here we have another example where I think this is just sort of general privatization. Again, here's the baseline. We can apply various combinations of these optimizations, and you can definitely get a measurable improvement here. Here we have our example from a few minutes ago, where we were able to inline and combine. And again, you can see this is the baseline, and then applying various combinations of these optimizations. Most importantly, the alias information and privatization can result in a fairly significant speedup over the baseline in this case. So I mean, the goal here, there are a couple other examples. The goal here is that we would like to be able to have a sort of easily maintainable and extendable way that applies to multiple programming models of performing these kinds of optimizations. And as I said at the beginning, given the kind of way that people are changing their codes and the way that uses of OpenMP and other things are changing in the future, I suspect that these kinds of optimizations are going to become even more important in the future. And some of this is cyclic, right? I mean, if the compiler gets better, then people write code assuming that the compilers are not silly, and thus the optimizations become more important, et cetera. But we already have cases where these kinds of optimizations can produce significant speedups. So I'm going to sort of present a couple of slides about sort of directions on for experimentation for research and for development. So here is a scheme which is based on some work that Intel has been doing internally. And what they've done is they have added a set of intrinsics to the IR, and they use them to denote parallelism directives. So they use them to, here I have an example. They use these intrinsics in order to take the OpenMP pragmas, clauses, et cetera, and provide those directly to the optimizer. And thus they can write optimizations that act on these, and they can then, after doing analysis and optimization, only then transform things into runtime calls. And one of the things that we've been thinking about is how to do this, but how to do this in a way such that we can write optimizations that are not programming model specific, but operate on an abstraction above that so that different programming models can be handled when they have equivalent optimizations that we'd like to perform. Those optimizations can be done in a uniform way on top of some abstraction layer. Now, obviously, there's a bunch of work that has to be done in order to make this actually functional. So as you can see here, they use these operand bundles. The bundles have names, but obviously some of these names have semantics. And so, I mean, this looks like it's something that's easy, right? But it's not actually entirely easy, right? Because you have to define these intrinsics so that they have properties that respect the semantics you need on the various clauses and such. And one of the things that we've been working on is figuring out exactly what those semantics would have to be. You can imagine, for example, there are issues that come up when you do inlining, when you like if you have stack allocations that are inside parallel regions, you may not want to move them outside of parallel regions because now you've created shared variables and all sorts of other things that you have to work through. What Intel has done is they have implemented this, and so we're working with them to experiment on that. And the way they've implemented it involves a number of different phases, where they take LLVM in that form. They generate code from multiple different programming models that all kind of lowers using those intrinsics, and then they have various ways of turning those into appropriate runtime calls and such. And then on top of that, they have built some analysis passes and other types of abstractions that will look for the regions of code that are encapsulated by those intrinsics, or at least by some of those intrinsics that indicate blocks and other things. And then they have analysis and transformation passes that use this abstraction in order to operate on the IR in that form. OK, so that's one thing. Now, another sort of branch of experimentation comes from the work that's going on Tapir. And I'm going to present a couple slides here from George Steele at Los Alamos. But here, let me just show you. So here, we've been working with the Tapir representation. This is another extension to LLVM. It's, in some sense, at least it looks more intrusive because it adds new instructions. Whether it's actually more intrusive than the other one, I think remains to be seen. But this is sort of how this maps. So here we have a very small example where we've taken OpenMP tasks and we have mapped that onto this Tapir representation. And originally, Tapir was designed as an IR that sat on top of Silk and the Silk tasking runtime. And it's since been also ported so that you can put it on top of other tasking runtimes, for instance, the OpenMP runtime that we have. But in this form, I should say, again, this is something that is not a bunch of runtime calls, and it's something that the optimizer can understand to the extent that we teach it. And so different kinds of optimizations are possible, including optimizations that you kind of get for free, like loop invariant code motion and other kinds of things that we just get from the rest of the optimizer when it can understand what's going on. So here I have 3 quick examples. These are 3 benchmarks. There's an FFT benchmark, that's NQueens, this is Fibonacci. And the thing that I want to point out is the following. So the orange bar here is the way that Clang, by default now, generates OpenMP code from these benchmarks. So that means in the front end, you directly create calls into LLVM's OpenMP runtime library. The optimizer doesn't understand anything after that, so you're done. OK, so the blue bar here is Intel's compiler. I think it's version 17, but I'm not entirely sure at this point. And Intel's compiler, its optimizer does have an understanding of certain parts of its OpenMP runtime. Internally, it uses some representation that's more amenable to optimization. And it does perform some amount of optimization. And so you can see here that, in general, the Intel's compilation of the OpenMP code is more efficient than Clang's current compilation of the OpenMP code. And this is fairly consistent across applications and the like. OK, so now we have these 2 other examples, other bars here. We have what happens if you use the Tapir representation and then lower to the OpenMP runtime library. And then there's what happens if you use the Tapir representation and then lower to the Silk runtime on which it was originally constructed. And so you can see here that we actually get some very nice results. So if you use the Tapir representation, and then lower to the OpenMP runtime library, so it's the same runtime, then you can see that the result is either the same as or better than what the Intel compiler will do for that code. So that's obviously quite nice to see. And the other thing I point out is that OpenMP obviously has a whole bunch of features that Silk doesn't support, and there's a bunch of differences. But you can see here that just what the difference is if you look at what Tapir does on the Silk runtime, and that is sort of either the same as or more efficient than any of the other options. But of course, has a more limited set of supported features. So, but regardless, just using this technology, keeping the runtime the same, you can see that there's a lot of potential performance gain here by allowing the optimizer to understand what's going on with parallelism, and this is what we're now working toward enabling. Okay, so at this point, I would like to thank everyone, including the people who pay for all the work and all the rest of you who make all this possible. Thank you.
So now we have 5 minutes for questions. So, questions? Okay.
So how you, I'll just shout.
Okay.
You seem to be showing about a 10% performance improvement on the early stuff where you were optimizing.
Mm-hmm.
But that mostly, as far as I can tell, was coming from improvements in the code generated for the loops rather than from eliminating bugs. Is that correct?
I think it's mostly correct. So a significant fraction of the improvement did come from propagating, from privatization and then from propagating analysis information, which in some sense you could call both of those things, propagating information into the parallel regions. And then some smaller amount came from eliminating some of the barriers and things that resulted from combining the parallel regions. I mean, I'll point out that there were at least one case that I showed earlier where combining the parallel regions actually was it was better than the baseline, but not the sort of best combination of things. So there's definitely some cost modeling and other things that have to go into that. Yeah, I mean, the sort of uniform improvement certainly came from the information propagation into the regions. Yeah.
More questions? Have some more time?
In the front here.
Oh.
Hi. So in your repeating example, you had some function calls that were inlined, and then you kind of merged the parallel regions. Mm-hmm. Have you considered maybe doing it for function calls that are not inlined? Is it possible?
Yes, this is definitely possible. It requires, in some sense, one layer more of interprocedural analysis. But it's definitely possible and maybe desirable, right? Because you may want to perform these optimizations without actually inlining everything. I mean, so I mean, and this also piggybacks on the fact that in general we would like to have better interprocedural analysis and information propagation with an LLVM. Obviously, this is not the only case where that comes up. So. That's sort of plugs into a more general picture, but yes, it certainly is desirable to do this in cases where you don't inline the functions.
We have some more time. No? No one else? Okay. Thank you, everyone. Please thank the speaker again. Thanks, Howard.